Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to introduce the topics where we will be approximating the value of an expression. So in this topic, we're going to describe what we will be covering in the next sequence of topics, including evaluating a polynomial. Given periodic samples of an actual function, we will estimate the value of the function at a point, we will estimate the derivative at a point, and we will estimate the integral of this actual function over an interval. We will introduce the idea that these samples may either be exact values or they may be samples that are combined with significant random errors. And we will describe how in both of these cases we will have completely different approaches to making the above three estimations. We are going to start this topic by looking at how we can approximate the value of a polynomial at a point. This might seem easy. How do we evaluate a polynomial? We just plug in the value of x or t and calculate. However, there are better and worse ways of doing this. For the next three subtopics, what we're going to do is we are going to try to approximate properties of actual real valued functions that are functions either of space or of time, represented by f of x and or y of t. Now, we are going to be sampling these functions at equally spaced points in either space or time. So the equally spaced points in space will be represented by x sub k, where we have an initial x value, and to that we add k times h, where h is the distance between sampling points. Alternatively, we may sample a signal or value in time. So we have an initial time, and we continue sampling at that initial time plus k times delta t. Now, if we are describing the exact value of the function at these times that we are sampling them at, we will write these points as, for example, x sub k and f evaluated at x sub k. That's the actual value at that location. Or alternatively, t sub k and y evaluated at precisely that time. These are the exact values. So in some cases, we can actually trust exact values, such as, for example, when we define the functions in a model and then proceed to simulate it. Now, if, however, we are sampling the values of these functions through sensors which consequently have some sort of random error associated with it, then the value of the sample is going to be represented by f sub k or y sub k respectively, based on whether or not we're sampling in time, space, or time respectively. What this means is that f sub k is not the exact value, but rather an approximate value where the error is assumed to be random. The same with y sub k is an approximation of the actual value, the actual temperature, the actual voltage, whatever we're measuring, of at time t sub k. Now we will start with the exact values. So we're assuming there's negligible error in the either f of x value or y at t value. Consequently, with these exact values, we will try to approximate the value of an interpolating polynomial at a point. So we've sampled these or made measurements at equally spaced points in space or time. And what we will now do is find a polynomial that interpolates those points and then evaluate that polynomial at a point. Next, we will approximate the derivative of the function based only on the periodic samples. Finally, we will approximate a definite integral at the points. Now, exact values may be used when we run simulations. After all, we may have a function that describes or models, for example, the potential difference across a battery over time. Exact values may also be the result of a solution to a simple differential equation with initial or boundary values. And this is what you're going to cover in your calculus course. So this is where we are assuming that our values are exact, and then we will see what we can approximate assuming we have exact values. Following these three subtopics, we will now, however, realize that if we are reading a sensor in the real world, there's going to be random error, and there may in fact be significant random error in our samples f sub k and y sub k. So we don't know what the true value is. We don't know what f is. We just know that we have approximations of those true values. I may have a GPS location as to where I currently am. That's likely not going to be where I actually am, which is the location I would like to approximate. You've actually noticed this perhaps. You will notice that in Waze or Google Maps, it seems that it can detect which lane you're in, even though the error for GPS is larger than that of a single lane. So how can it tell which lane you're in? So what we're going to find is that the previous approximations that we found using exact values will actually be useless. Instead, what we are going to do is we are going to use linear algebra and introduce the concept of something called least squares best fitting linear regression. The least squares best fitting linear or quadratic polynomials will significantly aid us in using our approximate values f sub k or y sub k and finding better approximations of the function at t sub k or x sub k or t sub k, or finding the derivatives or the integrals of these functions over time. Following this topic, you now have an understanding of the ideas that will be covered in this topic. In addition to determining how to simply evaluate a polynomial, you understand that we will be looking at functions that represent actual values in the real world. And these will be functions either of space or of time. These exact functions are represented by f of x or y of t. You are aware that we will only be able to sample these actual values periodically. So either in space with a difference of h, or periodic throughout time with a difference of delta t. You understand also that these samples may either be exact, represented by f at x sub k or y at t sub k, or these may be readings that are assumed to come from sensors that are combined with random error. So f sub k is assumed to be a sample of the actual value f at x sub k, but combined with error so that it's no longer exact. And that error is usually assumed to be quite significant, up to 10% relative error. You are aware that we will then try to approximate the value of polynomials interpolating these points in both cases, the derivatives of these at these points, and the integrals over a sequence of these points. And the goal of all of this is to approximate as closely as possible the properties of the actual underlying functions f of x or y of t. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!